And welcome again. And I'm going to solve few simplest of the problems of rotational dynamics. In this picture, you are going to see a board of mass M1. Board. I think this should be the board. Mass M1 lies on a smooth horizontal surface. Okay, so the surface beneath is smooth. And on it lies a homogeneous ball of mass M2. That's fine. Ball, homogeneous ball, that is a solid sphere of mass m2. A constant horizontal force F is applied on the board. With what acceleration will the board A1 and the center of the ball A2 move in the absence of sliding between them? That means there must be friction between the board and the ball, because ball is going to perform rolling without slipping with respect to board. So there must be a force of friction acting between acting at the contact, whatever the contact point is at a moment. So there is a force of friction there must be friction between board and ball. On board is acted board is has been applied a force F towards this. That means there will be a force of friction on the board in this direction. So that force of friction will act on the ball in this direction. Okay, fine. It was an easy pick. Now I'm ready to solve the problem. I have a fixed frame of reference that is called laboratory frame of reference, whose origin is here, and I'm going to solve the problem in this lab frame, and it is at rest with respect to ground, so it is an inertial frame, so I can call it lab inertial reference system. And their x and y axis of the Cartesian coordinate system is shown in the figure. You can see here. Now, in the lab frame, the motion of the ball should be considered as a superposition of its translational motion and the rotation of the ball about the horizontal axis. This thing, cross horizontal axis passing through its center of mass, and I guess something, and that's all right. I can guess something, and whatever be the horizontal axis, I don't know what will be its angular velocity or angular acceleration. Angular acceleration will be definitely in this direction, because friction is providing the torque about its center of mass. So angular acceleration is in this direction, anti-clockwise direction. I don't know anything else, and I don't want to know. So I have shown all the forces acting on the ball and the board. So free body diagram is complete. Let's move to the second step to solve the problem. And what should I need to do now? Okay, I'm going to write down the equations of motion. So first I'm going to write down the equation of motion of the ball itself, and it's in my inertial frame of reference. This is only acted upon by a force F as friction force. सिर्फ बॉल पर सिर्फ friction force लग रहा है. So I'm going to write down the equation of the ball, the projection of the forces on the x-axis only. So I am going to write down F equals m2a2. A2 is of course the acceleration of what is called the acceleration of ball towards right, and A2, yes, A2 I taken towards right at will. So force is acting in the, I am going to write down this equation. I don't know anything much, so I'm not worried about. And in vertical direction, in case I need it, n equals m2g. though I'm not going to need it immediately, but I can need somewhere at some moment of time, some point of time, so that's fine. And board also moves towards right. Let its acceleration be a1 in the direction of positive x-axis, and it is moving under the action of force F and the friction force from the ball, which is towards left. So I'm going to write down the equation of motion, and I left the equation of motion, equation of rotation, equations of moment for the ball, because these are the equations of motion of center of mass of the ball, 1 and 2, equation 1 and 2. This is a good practice. I have habit writing first the equations of center of mass of a rotating body, and this is the equation of center of mass, because center of mass represent a body for its translation. So these are the equations, Newton's second law of motion for translation. And I'm going to write it down for the board, and board is only translating, so no problem at all. Board equation is F minus F equals m1 a1. This is equation number 3. A1 is the acceleration of the board. Okay, I'm now going to write the equation of moments, torque equation for the ball, of course relative to its axis of rotation, passing through its center of mass and perpendicular to the plane of motion in which I am watching. You must be watching as well. And the torque is produced only by friction force, and so its torque is simply F multiplied by R about the center of mass, and that will be equal to its moment of inertia about the axis of rotation that passing through its center of mass. Sometimes it is written I naught or ICM. It's a good habit to write down. And its angular acceleration as beta. This is equation number 4. And now I need something else, because equation number 2 is not going to help much. So we got 4 unknowns and 3 equations, so we need one more equation. So I'm going to supplement this system of equations of motion of the ball and the board by a kinematic equation. And kinematic equations, what should be this? This is the point of contact. This is the point of contact of the board and the ball, and it is at rest with respect to the board. That means it is accelerating towards right with an acceleration a1. So उसका acceleration a1 होगा point of contact का with respect to ground in lab frame. And what if I see from the point of view of ball? If we let me place an observer here at the board, and its acceleration is let me place an observer at the center of the ball. Center of the ball. Okay, and so its acceleration, angular acceleration, is like in this direction. So because this acceleration, this observer will only be able to see its rotational motion, and for this its acceleration beta is in this direction. So this point will have an acceleration towards right, that will be beta r or r beta, whatever it is. And with respect to ground, this point should have an acceleration a2 plus beta r. So a2 plus beta r by using the superposition principle, and a1 by directly visualizing it, and a1 should be equal to a2 plus beta r. That means a2 equals a1 minus beta r. a2 equals a1 minus beta r or r beta, whatever it is. And its moment of inertia is 2 by 5 mr square. Right? Am I right? Right, I am. 2 by 5 mr square is the moment of inertia. And I got all those things. I can get now the value of A1, the value of A2 and everything else. So anybody can do. I thought, what was the value of A1? Whoa, notebook. Yes. The value of A1 you will get, that should be 7F upon 7M1 plus 2M2, and the value of A2 should be 2F upon 7M1 plus 2M2. And in case you need the maximum value of F max, sometimes are asked what will be the maximum value of F. So in that case you are going to use the friction condition, because there is a static friction acting between them. Static friction means a maximum is always coming on your way. So, and we all know that static friction, maximum value of static friction is mu1, so that we always write F is less than equal to mu1. And after you get the value of N, that was already we had it, the value of N somewhere written, and then you will get the F max by putting all things together. You will get something F max by utilizing this condition. F max, what was the value of F max? It is mu g 7m1 plus 2m2 by 2, and that's it. This is a simple problem.